Those of you in the internet, can you hear me? Okay, good. Are we ready to start? Okay, let's get started on this tutorial. Our first tutorial, week 1 tutorial. So the question here. Okay, this is our first question, question 1. That you are given that you have a charge Q1 located at location x equal to a, y equal to 0, and z equal to 0. You are asked, so let's try and solve question 1, part 1 first, part by part first. So if you look at part 1, it says find the electric field intensity E as a vector at the location x equal to 0, y equal to 0, z equal to 0, due to this point charge Q1, right? Yeah, so this Q1 is your source point, and then your observation point, right, is where you want to find the electric field, which is at the origin. Do you want me to go over this question, or it's clear how to solve it? Anyone want me to go over question 1, part 1? Okay, so Jorel, you do want me to go over? Okay, so maybe the question would be that where do you start, right? How do you start? How do you start? What do you all think? How do you get started on this? Point charge, okay. So you get started by taking a blank sheet of paper and start drawing your some figure, right? To see where is the electric field. Yeah, because you want to find the electric field. Okay, so if you take a blank piece of paper and start drawing now, one question will arise is, should you start drawing a 3D or should you be drawing a 2D? What do you think? Yeah, for this question, you can be just 2D. Why? Why is it so? Yeah, exactly. Everything is at z equal to 0, right? The charge is at z equal to 0. The E field you want to find is also at z equal to 0. So even if you draw a 3D, you'll collapse into the XY plane, right? The problem will just collapse in the XY plane. Okay. So let's do that. So let me start with drawing. Okay, so I started drawing the I say that I'm going to draw just 2D, x positive axis, y positive axis with z equal to 0. So it's a xy plane with z equal to 0. Okay, and our Q charge, point charge is located here at x equal to a, y equal to 0, z equal to 0, located here. So how do you see the electric field? Where's the electric field from that charge? You will radiate outwards from that charge or inwards into the charge? Outwards, why? Why is it outwards from that point charge? Yeah, exactly. It kills on, it depends at the end of the day, what is the value of your Q1, right? Is it a positive number or is it a negative number? So by default, when we visualize, when we put a variable like Q1, whatever variable we call it, by default is positive. Okay, by default is positive. Hence, by default, the E field will radiate out in all direction from Q, that positive variable. Okay, so that's what I did here. I drew some arrows to illustrate that the electric field will go out from this positive charge in all directions. So we are basically interested in the E field that will radiate out and eventually reach the observation point that we want, right? We want the observation point at the origin, right? Okay, so therefore, the arrow, the E field arrow that goes from the Q charge, right, all the way to the observation point in that direction is labeled as the R vector. Yeah, that is your R vector. Okay, so where is that R vector in the equation? So next thing we need now is basically the equation for the electric field. Okay, so here is the electric field equation for point charge. The electric field as a vector is given by a constant 1/4 pi epsilon naught times the total charge, which in this case is Q1, times the R vector. So this is the R vector. Now you can see visually on the figure, where is the R vector? Then divide by R cube. Okay, so this in the denominator is the magnitude of the R vector cube. Magnitude of the R vector cube, right? Okay, so do you all know how to get this formula from the exam appendix? Okay, all okay with that now, right? I don't need to illustrate to you how to get that. Huh? Just remember all this kind of formula, you don't need to memorize it. It's given in your appendix, exam appendix. Okay, so you tell me what is this R vector value? So the way you calculate a vector is the vector has a length. What is the length of R? A, right? This is located at x equal to A. So from the origin to this point is A, right? So this physical length is A, right? The scalar part of this vector is A. Direction is? Yeah, negative AX, right? So that's why we have R is negative AX. The magnitude is A, the direction is minus AX, right? Okay. And then, as I said, in the denominator here is the magnitude of this vector. So magnitude is just the coefficient of each of the unit vector, square it and square root, right? So in this case, we only have one unit vector, nothing else, right? So it's just A. And then you put that in, you got your point charge answer, right? This is the point charge answer. Okay with that? Okay, so I emphasize again, you want to draw that figure, visualize the electric field. Then you can see in the equation, where is the R vector? Yeah, if you just start off and use some metrics and solve, if you get the direction wrong, you may not know. Yeah, but visually you can see whether you're right or wrong. Okay, so the next part of this question, part 2, says that you are asked to find the electric field. In this case, we call E2 as a vector at the same observation point at the origin, x0, y0, z0, due to the line charge only. Okay, so where is the line charge? The line charge of length 2L is situated at x equal to minus A. Okay, so let's again go to the figure and draw it, right? So let's go back to the figure. Okay, so x equal to minus A is here. So I draw a line. In this case, I use a different color to illustrate it, red color to illustrate it. and the length of that line is 2L, right? With its center at the with it centered at the x-axis, right? Okay, so therefore it varies from minus L to plus L in y value. Agree? Okay, so now that we have drawn the line charge in that xy plane with z equal to 0, what's the next step? What do you think? What's the next step? Anyone? What would you do next? Find the DE. So what do you mean by that? What do you mean by that? What are you actually doing? Why is it called DE? E is electric field, right? So you're finding a small electric field, right? So in other words, you are basically identifying a particular point charge along that line. So basically what we're saying to ourselves is this line charge, we're going to chop it up into very, very small length sections that we are cascading, from minus L to plus L in y-axis. So when we chop it small enough, it can be considered as a point charge. So that very small length is basically your so-called DL length, right? Now, which point charge should where is the location of this point charge you want to choose? Along the line, yes, that's very important. It must be along the line. But where along the line? Some
the y value is variable and x value is next to A, and z value is 0.
Yes, excellent. Okay, so always choose it along the line. So along the line, you in this case, along the line charge, right? In this case, the z value is 0, right? We know, and the x value is minus A, right? The y value, we choose it to be a positive value. Choose it to be a positive value, okay? Y is a positive value, and it is a variable. So we choose it here in the positive y-axis. We choose it here. So the location of this point charge is at x equal to minus A, y is equal to some y variable, z is equal to 0. So eventually we're going to allow this y variable to vary from minus L to plus L. Okay, so having chosen that point charge, the next thing to do is to draw the E field, right, from this point charge, right? Where is the E field from this point charge? Again, you radiate out in all directions radially, right? The one that actually travels all the way to the observation point is this vector here, right? This arrow here. That is your R vector. That's your R vector for that point charge. Remember how, earlier on we also solved, part 1 is also same thing, right? So in this case, the R vector is here, right? So same thing again, we're going to use that point charge equation. So the point charge equation, remember, is this equation here, right? This equation here. So 1 over 4 pi epsilon naught is still there. It's still the free space epsilon. The total charge, tell me what's the total charge for this point charge? What's the total charge for that point charge? Okay. So in short, we need the line charge density, right? Rho L, which he has correctly pointed out, because we know the total charge of the line is Q2, and the length of the line is 2L. Hence, we can calculate the line charge density, assuming it's uniform. It's given that it's uniform, right? So therefore, line charge density is Q2 divided by 2L. All agree? Okay, so with that line charge density, how do you calculate the total charge of that point? you have to multiply by length, right? What is that length? Yeah, that small length, right? In this case, it should be labeled as dy, right? Because it's along the y-axis, not dl. Huh? It should be labeled as dy. All agree with that? Okay, so therefore, the total charge of this point charge is rho L times dy, where rho L is equal to Q2 divided by 2L, right? Okay, so therefore, that's why, I have this here, right? 1/4 pi epsilon naught Q2 divided by 2L times dy. So this is the total charge of the point charge. And then multiply by the R vector or R magnitude cube, right? So this R vector, let's call it R2. So this is the electric field due to that small point charge along the entire line, right? So that's why we want to differentiate, we want to distinguish it by using a small electric field. So that's why this D in front. Okay, so can you tell me, looking at this figure, what is R2 vector answer? So the way to do it is you decompose that vector into all the unit vector along the axis. So remember, in this case, we have rectangular coordinates. So therefore, we have x unit vector, we have y unit vector, and z unit vector in general. So you decompose this R2 into x unit vector means you move along here parallel to the x-axis, right? Move along here until you reach here. And then you come down, right? Vertically in the y-axis, right? In this direction, right? Then you are basically getting this R2 vector. Agree with that? So you tell me this vector from starting from this point charge to hit this y-axis along, moving along the x-axis. What's the magnitude you move? A. Direction? Direction? Yeah, positive AX, right? And then the one moving down, what's the magnitude? This one here. Y, right? Yeah, Y. And then the direction is negative AY, right? So therefore, that's how I have this R2 vector is AAX minus YAY. Use matrix and solve it, or you should get the same answer. Huh? Your field point minus your source point. So like I say, I like it to be visualized because real life problem is always solving some real thing that is a real life figure. Okay, so if you put this R vector into this here and the magnitude, okay, so how do you get the magnitude? In this case, each unit vector coefficient square, right? So I have A square and then plus minus Y square, right? So therefore it's also Y square, right? And then you square root the whole thing, right? So that's why A square plus Y square square root. Right? Okay, so when we put this in here, therefore that's why you see this term here, right? You see this term here. And then this charge Q2 over 2L, and then 1/4 pi epsilon naught, these are all constants. So I put them outside here. And then you have this dy here. Okay, so that is for dE. So in order to get the total E field, what we need to do is we need to sum up this dE, right? Starting from the one due to the charge here, all the way until you sum up to the top here. So therefore, in mathematics, this summing is equivalent to an integration. So you have to integrate from y equal to minus L to y equal to plus L to get all that summed up dEs. So therefore, that's why by adding in this integration with respect to dy from y equal to minus L to plus L, now my electric field is the total electric field already. Yeah. Is everyone okay with that? How that is formulated from up here, the dE, right? So it's all you have to do is just integrate. in the direction of the y, right? So that dy, yeah, for y equal to minus L to plus L. Okay, so now is a maths problem now. How do you do that integration? I think all of you know how to integrate a scalar, right? But that's a vector. So what do you do? Yes, exactly. Separate them into the two unit vectors or whatever number of unit vectors that has. You have to separate each of them. Each of them become a scalar. Okay, so that's your next step. Hey, very good. Very good. Can the rest of you also please actively participate? You learn a lot more if you actively, echo out what is in your mind. Echo out what is in your mind. Don't worry if it's wrong. Right. Okay, so that's what happens. We separate the two integral. I mean the two unit vectors, separate them. Yeah. So therefore now we have two integration to do. Okay with that? So now you start to go and integrate. Okay, so AX component, you know how to integrate this? A is a constant with respect to y. So therefore this is same like integrate 1 over a squared plus y squared to the power of 3 over 2 dy. Yeah, this integral. You know how to integrate this? Those for maths, A-level maths, you should know how to integrate this. This is a typical one of the A-maths question. Okay, so but in this case, in the tutorial, you're given the answer, right? The answer of that integral is this, right? So just use it and then substitute your y varying from minus L to plus L, right? Yeah.
Later during the finals, will they give those kind of identities too, or do we need to remember it ourselves?
You sound like you're from A-levels, right? Why do you worry? You should have practiced enough already. Okay, go in, look at past year exam paper. As far as I know so far, we are all kind enough to give you like your tutorial. Yeah. Yeah, because we don't want to test your maths. Yeah. Okay, so after that, all you have to do just substitute the y value, right? Plus L, right? So you have plus L over a squared divided by square root of, a squared, square root of a squared plus L squared. And then you minus, and then bracket, you substitute this y equal to minus L. So you have minus L. So it becomes plus L again, right? So that's why it's 2 times. Yeah. Okay, so we have this. Now we proceed to this one. You know how to integrate this? Do you know how to integrate this? Those from A-levels definitely should know how to integrate this. It's a simple integration. Those from Polytechnic, can you integrate this? How many of you here from Polytechnic? Can I have a show of hands? None. No one from Polytechnic. Really? All from A-levels. If you don't tell me, I'll just assume you know. You tell me, then at least I'll try and elaborate to you how to do the integration. Also quiet. So I assume you know how to do the integration. And then when you substitute the value of y equal to minus L to plus L, you should see the answer is 0. You should see the answer is 0. Agree with that? Agree, huh? I see number on head nod. Huh?
Because symmetrical along the axis of x, so this part cancel out each other.
Okay, okay. So anyone here don't know how to integrate this? If you don't know how to integrate this, you solve it like what he said. If you're powerful in maths, you know how to integrate this, you get the answer is 0 for the AY component. Just treat it as a maths problem. In real life, sometimes some integrals are so complicated, not possible to have a closed form kind of solution. Then in real life, we use a computer and solve it, numerical integration. And you find the answer is 0, if you like. Alternatively, you reason it out from the figure itself. Go back to the figure and reason it out by symmetry. So just now, when we consider this point charge, we say, hey, this point charge can be decomposed into an E field that has an AX component, right? Positive, right? And a negative AY component, right? So when you consider the one symmetrically on the opposite side, the R vector will be like that, right? For the E field. So again, you will have positive AX direction, right? But in this case, a positive AY direction. And you can see by symmetry, this length and this length is the same. So they will cancel each other. So that's why AY is equal to 0. So you can reason out from there, rather than doing the integration and show it's 0. Up to you in the exam. If you reason it out that way, we also give you full marks. Yeah. Okay with that? Okay, so now let's move on to the third part of the question. Third part of the question says that find the relationship between Q1 and Q2 such that your total E field at the origin is 0. So what do you do? Equal them for 3 unit vectors, okay? You have to equal them for AX unit vector. You have to equal them for AY unit vector. You have to equal them for AZ unit vector. But fortunately for this particular problem, yes, AY is 0, AZ is 0. That's why you only have 1 to equate. You only have 1 to equate. Okay, so the third part is that we have this. Yeah, so we want that the total E field is equal to 0, which is the E1 vector plus the E2 vector, right? In short, that means we say that the electric field due to the different charges are aiding vectorially. Yeah. So we want that equal to 0 in this case. So therefore, like I said, the vectors have, in general, in this case, AX direction, AY direction, AZ direction in general. But so happen in this case, the E1, E2, both the AY and AZ are 0. So we only have 1 to equate, the AX one. And hence from there we can find the answer. Okay with that? The part? Any questions, anyone, for question 1? Okay, so basically we start from point charge to derive the to find the E field at some observation point. We then extended that to a line charge, still uniform line charge. What if it's a non-uniform line charge? Any difference in the working steps? What if I tell you rho L equal to 6x in terms of the it cannot be 6x, right? It can be 6y in this case. Yeah, 6y. What if it's 6y, the rho L? Yeah, it's just the integration part, right? Yeah. Very sharp. Okay, now let's move on to question 2. Okay, so we have a square. Now we're extending to a surface now, right? We have a square conducting plate of side length 2a, positioned in the XY plane, centered at the origin, charged with a uniform surface charge density of rho naught. Why does it have to be a conducting plate? Can it be a non-conducting plate? Can also, right? Doesn't have to be a conducting plate, right? The conducting plate will force the charge density to be uniform now, that's for sure, because it's conducting. It doesn't have to be. Okay, so let's draw again, right? Our starting point is to draw again. So please take a piece of paper and start drawing. So in this case, can I draw just a 2D drawing or I need a 3D drawing? It has to be 3D because although the source, yeah, which is the conducting plate, is in XY plane with Z equal to 0, your observation point that you want to find the electric field is at 0, 0, Z, right? So it's at some Z value. So hence we have to draw a 3D drawing. Can you all start drawing a 3D drawing? Because it's a, some people may find it challenging to draw a 3D drawing. Okay, so for me, I decide to draw the x-axis towards me. So I call this the positive x-axis. And this one, I call it the positive y-axis. And then after I draw this x and y-axis, I use my right-hand rule. The fingers curl from x into y. The direction of my thumb of the right hand is the direction of z. Okay, so make sure you do that test to find out the z direction correctly. Okay, so we say that we have a conducting plate, center at the origin, length 2a on each side, right? So therefore, you will vary from plus a. By the way, this I label incorrectly, so be plus a. All the way to there is minus a, right? The behind is my x equal to minus a. And then this one is y equal to plus a to y equal to minus a here, right? So this is the conducting plate at z equal to 0. We're trying to find the E field at this point, 0, 0, z. x0, y0, z equal to some positive value. So by default, every variable we assume is positive to visualize. Okay, having drawn that, what's the next thing? Just like in the line chart, first thing we do is generalize it to a point charge first, right? So same thing here, generalize it to a point charge. So that means make the length small enough. In this case, you have x length and y length, right? Which we call dx and dy. So we call it dx length and dy length, small enough that this become a point. So where is this point located? Yeah, some x variable and some y variable in the positive side. So it should be in this quadrant that you visualize it. Yeah? Some positive x and some positive y. That x obviously is a variable. Later on we'll vary from minus a to plus a. And then the y also, we're going to vary it from minus a to plus a, right? Okay, so having drawn where that location of that point charge is, now you basically visualize where is the E field. So same thing again, it's going to radiate out in all direction from that point charge. You track the arrow of the E field that arrive at your observation point. So you agree with me, is this arrow, right? Is that is your R vector. That's your R vector in that point charge equation. Okay, so our same thing again, we're going to use that point charge equation, 1 over 4 pi epsilon naught, because it's free space. If it's not free space, this is basically epsilon R times epsilon naught. epsilon r is the relative permittivity of the material or the medium, right? In the material in the medium. Okay, so in this case, we are given that the surface charge density is rho naught. We multiply by the area of that small point charge, which length dx and dy, right? So rho naught times dx dy is the total charge of that point charge. And is located at x, y, z0, right? So from there, we can then have that r vector, and the denominator is the magnitude of that vector cube. Okay, so can you tell me the r vector answer now? So do the same thing again, decompose it into the ax component, ay component, az component. You agree with me that, you know, from this point charge, I should go parallel to the x in this direction, and then this direction, and then up, right? Eventually I reach here, right? Okay, so what's this x component? This ax is magnitude is x, direction is minus ax. Okay, this one y, direction minus ay, right? This one z, direction positive az, right? Okay, so therefore that's why I have this answer for my r is minus xax minus yay plus zaz. Okay, so what's the magnitude? Magnitude, again, remember, is just the coefficient of each of these unit vectors square. So I have a square, x square plus y square plus z square square root, right? Okay, after that, I'm going to basically put all this in here, right? Put all this in here. Okay, so you can see 1, 2, 3 after splitting it out for ax, ay, az. And then, of course, the constant of rho naught over 4 pi epsilon naught is also there. It's outside here. And then the dy dx or dx dy, when I get the total E here, I have to do double integral, right? So that's why you can see a double integral for x equal to minus a to x equal to plus a, and then y equal to minus a to y equal to plus a, right? That's what we have. Those are our limits. Okay, at this juncture, there are 3 integrals to solve. Okay, okay, before that, so just now I say, you know, I'm going to do a dx, then a dy, right? So we're going to integrate with respect to x first and then y. Okay, so let me illustrate to you what happens when we integrate with x first. So when we integrate with x, you're summing all these charges along this line, right? The column, if you like, right? At the end of the day, you have this line charge when you do a dx first. And then after that, when you do a dy, basically you are, you know, basically summing up all those lines across, right? Like that, right? In the y-axis to get the eventual total E. If you reverse the order, dy dx, what happened? Dy dx, if you do a dy first, you'll be forming across first, like that, right? Yeah. So you're forming a line in a row, line charge in a row. And then after that, you're summing in x, right? So we eventually will get you back to the same sum. However, in real life, if this geometry is not symmetric, you may find that in one case, do a dx and dy, you can have a solution. But do a dy dx, you have no solution, or vice versa. It depends on the geometry. Sometimes also it gets more difficult. It just, when I say no solution, means you don't know how to have an analytical equation. Of course, you can do it numerically. Yeah. So in real life, very often when we have this kind of double integration, we try integrate dx dy, it doesn't work, do dy dx. After enough practice, you know what kind of symmetry you should change. Yeah. Okay with that? Okay, so now finally we come back here. We just go and do a dx dy now. So in this case, we're going to do dx dy And because there are 3 unit vectors, ax, ay, az, you go and insist on and go and solve it by integral, like a maths, you're going to waste a lot of time, especially in your exam. So try and work smart. Which one will cancel and get 0? So you have to go back to the physical diagram to see that. So just now we say when we look at this R vector, right? Due to this point charge here, it has a negative AX component and a negative AY component, right? If you consider the same symmetric charge over this side, right? You will have a positive AX component and a negative AY component, right? So you agree with me, basically all those on this side, right, of the x-axis and those on this side of the x-axis will cancel each other to make the x component 0, right? But the y component won't be 0, yeah, when you do that, right? However, when you start doing integration with y, you can see that this line charge over here will have this negative y direction, but the line charge over the other side will have a positive y direction, right? So again, they will cancel each other. So in short, no need to go and solve those 2 integrals that involve ax and ay. You can argue from symmetry that they are 0. Okay, finally, the az. So just now we say the az is positive, right? From this one. From this one also the same, right? It come down, also go up, right? From this one also, right? You go there, also go up, right? This one also, right? Same thing, right? Go up, right? So effectively, if you just find it for one quadrant, you multiply it 4 times. Okay, so that's why we changed the formulation over here to start from x equal to 0 to a rather than minus a to a. And then y equal to 0 to a also instead of minus a to a. But you have to have 2 times 2. 2 from the x, 2 from the y. So that's your factor of 4. And why I want to formulate it that way? Because you're given how to solve this integral when your limits are from 0 to a, right? The double integral answer is like that. Those of you who are powerful in maths, of course, you can solve it and find the same answer. Okay with that? Yes. 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 Oh, because I have not canceled them, right? You can see, this 4 and this 4 cancel. Yeah, I have not canceled them. I deliberately leave it like that. Yeah. Yeah. Should be the same. Yeah. Well observed. Okay, so now let me ask you, what is the unit of electric field? Watt per meter. What does your FE 1007 tell you? Electric field, what's the unit? Newton per kilo ohm, right? Yeah, it's from the formula F equal to QE, right? So E equal to F divided by Q. Force is in Newton, charge is in Coulomb, so Newton per kilo ohm, which is equivalent to watts per meter. So for electrical engineers, we always use watt per meter. We don't use force over charge. Yeah. Okay, any questions, anyone on this? Jorel, you asked how to know y equal to a, x equal to a. I'm not sure what you mean, Jorel. Do you want to unmute and say? Are you asking about the integration limit, why we're integrating x from minus a to plus a, y equal to minus a to plus a? Oh, that's because the conducting plate is, I mean, you look at the figure, you see the figure, the bound for this conducting plate lies from x equal to plus a and minus a, right? Same thing for y, right? Plus a minus a, right? So that's why your integration is over those limits. Is that okay, Jora? Yeah, the length is 2a. Minus a to a is 2a, right? Yeah, total length is 2a. Yeah, this plate is centered at the origin. If it's not centered at the origin, is the answer the same? What if you have it, along the let's say the top edge is actually at the y-axis? Would the answer be the same? No, huh? No, unless you move the observation point also symmetrically to that center. Otherwise, you will have some other component already, right? You can see it from symmetry. Okay, any other questions, anyone? If not, basically, yeah, so our style is that the first part, we go over all the questions in the tutorial, which we have already done now. So the next part is to go over the lectures for this week, which means you need to have gone through it in order to solve the tutorial questions of next week. Okay, so I'm going to use that as a compass to see whether you got problems with the lecture notes. How about that? Good idea? Okay, so let's go and look at the question for next week. See whether you understand the question. If you don't understand the question, you have to go back to your lecture notes. Tutorial 2. By expansion in Cartesian system coordinates. What is Cartesian system? Yes, exactly. AX, AY, AZ. Yeah, the three unit vectors is known as Cartesian system. Give me another equivalent but not Cartesian. 3 coordinate system. Cylindrical, exactly. What are the unit vectors of cylindrical? AR, yeah, the radial unit vector. A phi, the angular. And then AZ. There's a third one. What's that? Spherical. Spherical. Spherical is you have again a radial direction. Yeah, a radial unit vector. Just like in the case of the cylindrical, the cylindrical is horizontal, but for the spherical, it can be at some angle. So hence there are 2 angles now, A phi and A theta. That's cylindrical. That's spherical. Fortunately for you, that's out of your syllabus. You're not going to get any exam on spherical. So that's why if I bring you to your appendix of your exam, let me show you the appendix of the exam again. And then we look at some other interesting things that you should know by now. Epsilon naught value is given to you there. Mu naught value is given to you there. There's something that is given to you is called the del operator. Yeah, this inverted triangle, the del operator. So this is your gradient V, the gradient of V. So it's a del operator operated on V. And you can see this is Cartesian, AX, AY, AZ. The equivalent for cylindrical is here. And this is also gradient V, but in cylindrical. AR, A phi, AZ. Note A phi, very interesting. You partial differentiate V with del phi, but the answer you have to multiply by 1 over R. Take note of that. The answer of after you get what del V over del phi, you have to multiply by 1 over R. And then it's in the unit vector of A phi. Very often we forget that because all the rest are just, you just partially differentiate with respect to that unit vector and assign the direction, right? You can see this one, all 3 the same, right? Okay, so this is gradient of V. This is read as the divergence of A. In this case, this del operator dot the A vector. Yeah, this is called the divergence of A, and is given by this. Can you tell me this del is it a vector or a scalar? Scalar, then that dot is just a multiply, right? It has to be a vector because it's vector dot product. Huh? It's a dot product of two vectors. So what's the del vector? Give me the del vector in Cartesian. It's basically just del x, ax, plus del y, ay, plus del z, az. That's the del vector. So now can you mentally solve that vector dot with the a vector? What's your answer? Do you see the answer? Yeah, you can see the answer, right? Ax is just saying, you know, basically your a vector is given by some ax coefficient times the ax direction plus some ay times ay direction plus some az in az direction. That's your a vector. So it's so-called generalized vector equation. Okay, the next one down here is called the curl of A. So again, it's vector cross. Huh? So this del again is a vector. Yeah, so that's why you see, you know, the how you cross two vector, right? You take all the coefficient of the first vector, del x, del y, del z, then the coefficient of the next vector, ax, ay, az, and of course on the top there you have each of the unit vectors. Do you all know how to expand this further to get the actual answer of the ax component, ay component, and az component of this vector cross? Yeah, you have to use the determinant. So let's. Any of you want me to go over that, or is clear how to find this vector cross? Anyone wants me to show you how to do a vector cross? Yes? Okay. Okay, so del is a vector. Huh? That's why for me, I would like to write with an arrow on top to prompt myself is a vector. Cross a vector. So these are all in Cartesian coordinates. So therefore, the top row is ax, ay, az, as we said earlier, given in your appendix. Next row is your del vector. Yeah? So that's why you have del x, del y, del z. And then finally, the last row there is your a vector, right? So ax, ay, az. Okay, so the answer of that is given by the determinant. So first thing you should do is this one here is a plus. The next one here is a minus. And then this one here is a plus. Okay, so next you write out this ax component. So now it's a plus ax, huh? Plus ax component, bracket this times this, minus this times this. As you can see. And then next you have minus ay component. Then you cross like that, right? So this times this, minus this times this. And then finally, last part is your az one, right? So az is again a plus, right? So plus az. So you have del x times ay minus del y times ax. Yeah, that's how you expand out that determinant. Yeah. Okay, that. Okay, so you can see in your exam appendix, all those three equations up here is Cartesian. The same tree for cylindrical. Down here is cylindrical. Okay. Yeah. So these three are for cylindrical. Same equations, but for cylindrical coordinates. So no need to memorize in short. Just always refer back to your exam appendix when you practice, so that you know how to use it properly. Okay, so now let's get back to our tutorial questions. And with that in mind, so you tell me this one, first part. They want basically the question want to tell you that the curl of the gradient f is 0. Curl of gradient f is 0. So this del is a vector or scalar? Vector, huh? So you're doing a vector cross product with this gradient f. Gradient f is another vector. Curl of a gradient vector is 0. That's what you want to show. Any of you got difficulty to start this? No? So how to show is equal to 0? Start from left hand side or start from right hand side? Huh? Obviously, right? It's start from right hand side, you're in dead trouble. It's 0. So how to start from left hand side? We saw what is there, right? As a vector. Then what do you do with gradient f? What do you do for this gradient f? Express it in some generic ax, ay, az components, right? And then start manipulating and show that it's equal to 0. Okay, that you have to think carefully when you do that. Yeah. Okay, so that's the first part. The second part, this is saying the divergence of the curl of a vector is 0. The divergence of a curl of a vector, right? So this is curl of the vector, which is del vector cross a vector. This is known as the curl of the vector A. We're finding the divergence of that result. So this is another vector, the vector dot product. You want to show that that is equal to 0. So same thing again. Obviously, you start from the left-hand side. You have the del vector and you have the A vector, which you're going to put in a general expression, right? And then manipulate until you show it's equal to 0. Okay with that? Okay, second one. Verify the divergence theorem. What is the divergence theorem? What is the divergence theorem? Okay, so let's go and look at the notes and see what is divergence theorem. I have downloaded each week all the slides. So this is the same as what you will go through in your video. I would suggest, you try and go through the slides. If you don't understand the slides, go to the video. Those of you who are relatively good student or strong student, the videos are just too slow. Yeah. Okay, you tell me, tutorial 2 starts from which section, which part? Those of you who have gone through it. From 6. Thank you. Good. At least I know he has gone through it. From 6. Okay, so let's go to 6, part 1. Okay, operations using del operator. So I skip all this. Any questions with this? I skip all this, huh? Okay. If you have questions, please ask. How about those on the internet? There's nothing on the screen. Yeah, just now I was on the visualizer. You have to really look at that small part in the in the screen, Daniel. I don't know whether are you okay now? You should be able to see the slides, right? Are you still there, Daniel? Online? How about previously, all those which I write on the visualizer? Unfortunately, it's kind of small. You have to see it from this camera view, one of the pinned, yeah. So there's not much I can do about the recording because the recording is going to be very small. You can't see it all. So if you don't understand, then please come to the physical class. Okay, so that's the first part. The second part on section 6 is this one, which is divergence and surface integral. Any questions on this set? Divergence and surface integral? Maybe I just go over first, and because we are looking for divergence theorem. Okay, curl, line integral, and summary of their operators. Still no divergence theorem. Looks like it's in the last part. Okay, Stokes theorem, divergence theorem, and null identities. Okay, so let's go through this one. Where are your divergence theorem? Stokes theorem. Yes, divergence theorem. Gauss theorem, also known as Gauss theorem. Can you read this out? Can you read out this? How will you read this? So let's start from here. What is this thing here? Del dot A vector. So it's finding the divergence of the A vector. The answer of this will be a scalar, I agree, because it's a vector dot product, right? And they are integrating that scalar over a volume, right? Okay. So when you find the divergence of that vector, that field, A is a field, okay? A is some field, vector field. When you find its divergence and that result, you integrate it over a volume, is equal to, what's this? Closed surface integral. Closed surface integral of that field, right? So A is the field, right? Field vector dot with the area vector, right? Yeah, the ds an is the area vector. Okay, so this is divergence theorem. So let me put it out. This is divergence theorem, huh? This one. I just rewrite it again. Okay, so we are given that we have some electric field called A vector, okay? Given by this equation in this tutorial 2 question. So it's saying that you have some AX component that is proportional to X times Y, and some AY component that's proportional to Y times Z, and some AZ component that's X times Z. So I just arbitrarily visualize them by the red arrow. Just arbitrarily draw it. If you want to visualize that more carefully, you will use the length denote, in the X direction, X times Y, right? And then Y direction, Y times Z, and Z direction, X times Z. It's just too tedious to do, unless you have a computer and ask the computer to plot it for you. Okay, so we have this electric field, if you like, yeah, it's the red arrow in this 3-dimensional space of X, Y, Z. Okay, now we're going to use surfaces to bound a volume. So in this particular problem here, we're going to use a cube to bound a volume in this 3-dimensional space. So this cube is going to be, you can see the cube in the x value, it lies from x equal to 0 to 1, right? And then y is from 0 to 1. Z is from 0 to 1. So that forms that cube. Okay, so that surface, all the 6 surfaces of this cube encloses the volume. What are the 6 surfaces? The front surface, the back surface, right side surface, left side surface, bottom surface, top surface. Those 6 surfaces enclose a volume. So just now, when we talk about this closed surface is closing up the volume over here. Okay, so we take the field vector A, that electric field, dot with ds. That means we dot with the area, like in this case, since everything is just a plane, then obviously you just width times length is your total area for the front surface. But if it's curving, then you have to do some integration, right? Okay, so in this case, you tell me where's the direction of that front surface? Yes, this an here, right? This ds is a vector, right? Which is the scalar quantity of ds times an vector, which is the direction of that small area. Where is that? If I have an area here, where is the direction of this area? Yes, always perpendicularly. If I have an area here, again, perpendicular to it, always perpendicular to it, and out of the volume that it encloses. So you tell me the front surface, where's the direction of the an? Positive ax. Okay, the back one? Negative ax, right? The right side? Positive ay, right? Left side? Negative ay. Bottom? Negative az. Top? Positive az. Okay, so in order for you to show this, in this second problem, so we have our left hand side, which is solved. You must show that it's equal to your right hand side. When you do the right hand side, you have to do 6 integration, double integration over each of those surfaces. Okay with that? And then if you can show left equal to right, that means you have shown that they are equal, which they're supposed to be according to Gauss theorem or the divergence theorem. Okay, so I think that's about it, right? That's about it. Okay, the next one is actually question 3. So one more, right? So the third one now is actually this is closed loop line integral. Okay, so if you look at Stokes theorem, just now this is Gauss theorem. Before that we saw Stokes theorem, right? There you go. Stokes theorem. Stokes theorem actually is one order less, right, in dimension. So earlier on, the divergence theorem, this is triple integral over volume. Now this is a surface integral. Surface integral. So that surface, this surface is enclosed by a closed loop line, right? Closed loop contour, if you like, closed loop contour. So you can see, closed loop contour of that A field dot the length along it, along the contour in a closed form. So the contour encloses the area, right? Which is the whereas the divergence, the closed surface encloses a volume. This one is a closed contour, encloses an area. Okay, so that's basically your third one, the third question in this tutorial. So first you're asked to find this closed contour integration along these lines, right? In this manner, right? So A is a field in this XY plane. Huh? You visualize A is some field in this XY plane. It could be a magnetic field, it can be an electric field, some field there in the context of our course here. And it's given that AX component is proportional to 2x squared plus y squared. AY component is proportional to 2xy minus y squared. So you want to show that the closed contour integration of that field A dot DL around this rectangle, right? So therefore you have this has got four segments. This, and this to complete the contour, closed loop contour. So this one, what's the direction? You can see it's AX, right? And the length you travel, of course, is 2. This one is AY, right? And then this is minus AX, right? This is minus AY, right? Eventually come back there. So that encloses the surface, right? So this, you want to find that, which is the curl of A, the A field, dot with ds. So it's a double integral to find that. So your answer is you want to find whether A is irrotational from that answer that you found. Okay, that one. Okay. Okay, now why are you learning all this? It's all maths. Everything is maths. Why are you learning all this? Basically, divergence will help you to, usually is applied to find the E field, because you find that the divergence theorem can relate to the total charge enclosed in that volume. And the curl is usually used to find the magnetic field. Yeah, but only for simple geometry. Your geometry complicated, you can't do that. You need some kind of symmetry to find this. Yeah. Questions, anyone? So I stop here? Yes? Any questions for those in the internet? Okay, with no question, I think, yeah. Read your ebook. I strongly encourage you go and read your ebook, because then you will cover a lot more how you apply all this. Because so far, I tell you frankly, I think we just cannot have it that kind of details, because a lot of students just too weak to be able to know how to use this. So you find that actually the questions are more on for you to realize how to use the maths, how to do the maths, because that's the basic. If you can't do the maths, you can't use it to go and derive the magnitude. Usually it's used to derive the magnitude of E field or H field. Direction, you still have to reason out from the symmetry of the problem. Yeah, so I strongly encourage you to go and read the ebook. The ebook is the one that I mentioned to you early on, to get some further understanding of how to apply this one. This one, Nathan, Ida. Like I say, it's an ebook, so you should be able to download it. But prepare yourself with heavy reading. Yeah. Any other questions, anyone? Okay, if not, I think I'll stop here. If you have individual questions you want to ask me, you're welcome to do so. I'll stop here.